Okay, let's get started. We have a lot to do today. I'm running a little late because I forgot my tripod, but make sure that you have turned in the quiz and then the bonus if you have it. Quiz. I have a handout for you. I haven't announced that yet, so yeah, I'll announce it in just a second. I am, I know. I'm not worried about it though. Y'all ready? Let's get down to business. Okay, so normally I have a set of notes that I hand out to you, and every time I sit down to try and make notes for this section, I realize that the most efficient way to do it is to just write. So I've given you formulas that I'll refer to throughout the class. I'll try and show you as much visual stuff as possible, but just be aware there are no notes for this section that I'm handing out, all right? Okay, so this section 7.2 is called volumes, and there are a few things preliminary that we need to be aware of. First of all, if you have a rectangular box, which the technical name for a rectangular box is a parallelepiped. If you have a parallelepiped and you want to know its volume, the volume is length times width times height. So here's my box. Call this maybe the length over here, then the width, and then the height would be this side. You multiply all three, you get your volume, correct? All right, if you take a right cylinder, okay, this is like a beer can, but a really flat-looking beer can. The volume of a right cylinder is pi r squared times h, where r is the what? Radius, and h is the height of that thing. So imagine there's a radius coming out of the center to here. Then the height is this side. The volume is pi r squared h. Pi r squared is actually the area of a circle, isn't it? So it's really like you're taking the area on top and multiplying it times how deep the thing is, right? And that's your volume. Then we have this thing called a washer, which is basically a cylinder with a center cylinder cut out of it. So if we wanted to know the volume of this washer, then what we could do is we could figure out what the volume of the larger one is, which would be, imagine from the center, the outside radius, which I'm calling R out. So from the center all the way out, do that radius, pi r squared times h. That'll give you the entire thing with nothing taken out, right? Then subtract from that this right here, which would be the smaller radius, that volume in there, cutting it out. Yes? Yes, there's supposed to be an h here. Actually, yeah, I'll put it right at the end. So if you factor out a pi and you can factor out an h, then you get this. All right, now this one is a little different. This is called a cylindrical shell. So it's basically this picture, but there's something more subtle that I want you to see with this. If you have this cylindrical shell, and I want to know the volume of it, could I use this formula up here? Yes, I could, couldn't I? I mean, it's the same thing. I have an outer radius. I have an inner radius. I have a height, which is the same. So I could use it, but I want you to see that there's another way that I could approach it. Right? So let me show you the other way. I'm going to do it on a different page. So imagine if I were to come in with this thing and I were to take, I don't know, cutting torch or scissors if it's made out of paper, and I were to cut it. Do y'all see my line? I cut it right here, all right? Cut it, and I fold it out and open it up, assuming it was flexible. Then it would look something like this, all rolled out, wouldn't it? It would have a little bit of a depth to it here. And that is a what? A parallelepiped, right? That's your rectangular box, or rectangular, rectangular box, that's fine. Parallelepiped. So what's the volume of a parallelepiped? Length times width times height. So let's talk about what that would be for us here. How about this right here, this little part right there? What would that be? That's equivalent to this little piece here, right? That's your outer radius minus your inner radius. R out minus R in. Agreed? Okay. And then how tall is it? H, we'll call it height, right? So I know two of the sides. How about this third side? It's the circumference, approximately the circumference of which circle? The inner one or the outer one here? Oops. The outer one? So what I'm doing is I'm saying if you look at it this way, you're roughly looking at a circle, aren't you? And so that circle's circumference is how long that parallelepiped is. The outer circle's radius would give us the circumference. So let me go back here. So this should be circumference, right? Which is, circumference is 2 pi r. 2 pi times r out. Do you agree? So what would the volume of that be? Just those three multiplied? So something like 2 pi h r out times r out minus r in. Do y'all see how I came up with that formula? Okay, we're not going to need to be able to use that formula as much as we're going to need to be able to understand the concept of cutting that cylinder open and laying it out and coming up with something, a formula based on that shape. Okay? All right. So those are our preliminary ideas. Now, like I said, I have some notes. They're general notes, but most of what I'm doing, I'm going to write down. Don't feel bad that I didn't print this out, all right? This is just to get us thinking. Suppose you take the area between two functions, which is what we did last class, right? We had two functions. They somehow bounded some area. We're on some interval, and we want to rotate that area, that region, around the x-axis. When we do that, it forms a three-dimensional solid. We wish to determine the volume of that solid. So here is a two-dimensional region, right? We have a function on top, we have a function on the bottom. We have this region between them. I want to take it and rotate it around the x-axis. So here's our x-axis, here's our y-axis. This is going to be three-dimensional, so here we go. I start to rotate it around, right? It would go like this, come around back to the other side. You all see that? All right, so now what I'm going to do is I'm actually going to trace out and leave a solid behind it as I rotate. All right, so when I rotate this around, I get this. And you can see that this solid has a hole in it, doesn't it? But it's not a straight hole, so let me clear that out. Now you can see it a little better, right? That's a weird looking shape, isn't it? And what we wish to figure out is what is that volume? All right? Any questions? All right, so how are we going to attack this? Well, let me first motivate the idea by not taking two functions like we had here. Right? We had two functions like this. Why don't we just take one function and look at the area all the way down to the x-axis instead? So something like this. Here's our function. When we were trying to find the area here, what we did is Riemann sums, didn't we? We cut it into a bunch of rectangles. The more rectangles we had, the better it was, right? Yes? So what I'd like to do is just look at one of these rectangles. Now, I hope you understand that rectangle is going to get smaller and smaller, eventually becoming an infinite number of rectangles. But let's just see what happens to a very exaggerated one. If I start rotating this around the x-axis, so it's hard to see I rotated it, right? But I have. So let me switch to more of a three-dimensional view. So I'm rotating that around, and you get something like that, right? Now, what shape did I just create with that? A right cylinder, right? And I know how to come up with a formula for the right cylinder. It's pi r squared times height, isn't it? So imagine we do that, but we do it for a bunch of rectangles. So you get something like that. That would be an approximate volume, wouldn't it? If I added up all those cylinders, that would give me an approximate volume. And how could I get an even better approximation? Smaller rectangles, which would mean thinner cylinders. So I put more and more cylinders in here, right? More and more and more and more, eventually letting the number of cylinders go to infinity. And that should converge to your true volume, shouldn't it? And so at the end of the day, what we're looking for, what we're looking for is the volume of that thing. Yes? So this is a less complicated version of this, right? This was a little bit more involved. But the concept is here. You're going to take a rectangle, you're going to rotate it. When you rotate it, it creates a cylinder. If we can come up with a formula for that cylinder, then we add up an infinite number of them, which means we're going to integrate, and we'll have the true volume. You with me? Okay, so let's get down to business. We need to come up with a formula. So let's start this off. I think we're going to start with the more advanced case, which means we're going to have two functions. We'll call the top one f. We'll call the bottom one g. We will look between two values, a and b. And I wish to take this region in here and I wish to rotate that around the x-axis. My x-axis is down here. Y-axis is up here. So I'll put up here so everyone knows what I'm doing. I'm going to rotate about the x-axis. I'm being very specific that we're rotating around the x-axis. There's no clickers. Okay? I'm being very specific that I'm rotating about the x-axis. Why do you think that is? What do you think we're going to do later? We're going to go around the y-axis. And even later, we're going to go around arbitrary lines, not just the axes, just some arbitrary line instead. So we have to be very clear on what we're rotating around. Okay. What's that? Yes, and it's always vertical or horizontal in this class. There's ways to do it around skew lines, but we don't touch that in here. Okay, so let's go with this concept again, that I'm going to start with the rectangle. I'm going to take that rectangle, I'm going to rotate it, I'm going to try and come up with a formula for that volume. So when I take this infinitesimally wide rectangle, right, and I rotate that around the x-axis, look at what I'm about to do. Next to my x-axis, I put a little, it's like a curved set of arrows. That kind of shows you your axis of rotation. It's letting everyone know I'm taking this, I'm going around the x-axis. What is that going to look like when I rotate that around the x-axis? A washer, right? A washer. It's going to look like this guy right here, isn't it? Now, it's actually going to look more like that, though, right? So I'm about to draw that. So next to this picture, on the side, I'm going to draw my x-axis again. I'm going to draw my rectangle again. So I'm taking out all the other fluff in the problem, the rest of the function. I don't care. I'm really just concerned about that rectangle going around this axis, right? So try and draw this washer. Well, you know what? Maybe we can try this. Wouldn't that rectangle wind up on the other side like this also? Right? I mean, it would be on the bottom eventually. And then I need to somehow connect this together with some sort of thing that looks like. This is not the easiest thing in the world to draw, but you do your best. I mean, roughly that's what's happening. Now, I've been doing it for years. Oh, that's terrible. It's still hard to draw on a piece of glass. Okay, so give me a break. If I were up on a chalkboard, this would look beautiful. Okay, so that's basically what I'm doing, okay? Now, tell me about the volume of this washer. Well, we need to know a couple of things, don't we? We need to know an outer radius, we need to know an inner radius, and we need to know its height. So let's talk about the outer radius first. What's the outer radius? That's from the center all the way to the top, right? That's my R out. And for us in this problem, it's actually f, isn't it? The function f. And what about the inner radius? That's R in, and that's g function. And what about the height of this thing? The height is actually like this little width of this rectangle, isn't it? And that's always been dx, hasn't it? Delta x. But we're going to go to the infinitesimal eventually, right, with an integral. So that width will be dx. So I'm going to label this width here, from here to here. That's dx. So going back to this formula, we're going to have pi times the height, right? The height's in the back. I put it in the back here. R out squared minus R in squared. So let me write that down here. The volume of this one little piece will be pi, what did I just say? R out squared. So what's that for us? The f function squared minus the R in squared, so g function squared times h, but h for us is dx. That is the volume of that one little sliver washer. Make sense? Now, if that gives me the volume of just one, I want the volume of the whole thing. That means I need to add them up, and I need to add an infinite number of them up, which means we're going to come in with an integral, right? And the integral is going to contain, as it's integrand, it will contain this formula. Right? So everyone clear that the volume I have right here is just the volume of that one piece. Okay, now let's go back to this bigger picture. If I were to take that and rotate it, the volume of this will be an integral. It'll go from a to b. It'll have pi, right? And then f squared minus g squared dx. Now the pi is a constant, so it can come out in front. Then you have f squared. Now let me write it technically so it looks better. When I say f squared, what I mean is you take the function f of x, and you square it. Then you take the function g and you square it, and then dx. This right here? F2x? That's correct, yes. That is correct. The only reason I don't do it is because, I don't know, students for some reason in the past have had trouble remembering that that's squared. I don't know. Most books do it this way too. Now I believe that on your sheet that I just gave you, the notes, did you get this? I jumped across, just look down here, it's the last formula on the first sheet. Volume is pi, a to b, f squared minus g squared dx, rotating region between two functions about the x-axis. Okay? That's what we're doing. So do you see where that formula comes from now? It's important not to sit here and just be like, oh, there's a formula, I'll just memorize the formula. It's important to see where the geometry of it comes from, because the problems at the end of this section require you to really understand the geometry in order to figure out the integral. All right, so just pay attention to it, ask questions if you have them. All right, shall we do an example of this? Okay. Let's, as an example, find the volume of the solid formed by rotating the region bounded by y equals sine x. Well, do we want to do it? Do we want to do it? Yeah, sine x and y equals cosine x x equals 0, x equals pi over 4, about the x-axis. Starting off with kind of an ugly one. So the instructions for this problem are kind of long. I can't just say like integrate, right? I have to tell you a lot. Find the volume of the solid formed by rotating the region bounded by these two functions, well, actually 4 curves about the x-axis. So we need a picture first, right? No pictures. I don't give you any pictures this time. So here comes my picture. Sine curve looks something like this. Cosine curve looks something like this. X equals 0 is a vertical line going through the y-axis. You agree? And x equals pi over 4. Where's that? It's where they cross each other? How do you know? You did that for your quiz, didn't you? Sine and cosine are equal to each other at pi over 4. That's why I made it pi over 4. So I want to make sure we're just looking at this region right here. Any questions? Do you want me to label those, or are you okay with them not labeled? We're good? Okay. All right, so now, well, I would expect you to label it, you know, on a test, so I may as well. X is 0, x pi over 4. So everything's labeled. So when I take that and rotate it around the x-axis, right, it's going to look like this. I'm going to come in with my rotation thing. I'm going to do my rotation little reference triangle on the left side because I'm kind of out of space on the right side. So I encourage you to do this for each problem. Draw your axis of rotation. Draw me a sample rectangle in here. All right, give me a little sample rectangle. Move it over to the side. And then I'd like for you to kind of label on here, like where that top of the rectangle hits that curve. It looks kind of like that. And the other one looks kind of like this. Do you agree? I'm kind of like magnifying this little section right here. Right? What is the top function? This is y is cosine x. And the bottom one is sine x, right? So we have the same concept of like this upper, like top function, f, and the bottom function, g. But I'm still going to draw it, all right? Look it. I've got the distance from here all the way down, right, is that's my outer radius, really, right, which for us is cosine x. I think right now you may be saying, okay, well, do I really need all that detail? Not necessarily for a problem like this, but later on, like I said, when we move our axis of rotation somewhere else, we need to pay close attention to what that distance is, because it may not just be cosine x. It might be something else. All right, next one. This to here is sine x. I'm even going to put a little more label on this. This is the R in. This one up here was the R out, right? Do I need anything else? Can we go straight to the integral now? Do you have everything? I think we do. See, the volume should be pi integral where to where? 0 to pi over 4 of the outer one, so cosine first, right? Cosine squared x minus sine squared x dx. And that's it. What's that? Yeah, so at this point, you just integrate. And how would you integrate cosine squared x? Because I would split this into two, maybe. Power reducing formula? Yeah, 1/2 times 1. So we could do the rest of this, couldn't we? Theoretically. Which is why, yes, dot, dot, dot. No more. I'm not going to take time to do that. Now, do we want to know what the answer is? Yeah, I'm sure we could, right? Yes. Not for a solid rotate around the x-axis. That using this method it would not. You would always have the pi in there because it's part of the volume formula, pi r squared h. Mm-mm. Nope. Nope. Yeah. Yeah. Again, not for rotation around the x-axis. It's going to be there. Okay, so no questions? We're good? We're good? Okay, let's try something a little more interesting, I think. Can anybody tell me real quick, what is the volume of a sphere, solid, okay, so a ball, radius r? 4/3 pi r cubed. Have y'all heard that, seen that formula before? The volume is 4/3 pi r cubed. Yeah? You could look it up, and you'd be happy with it. So the question is, now, where did that formula come from? So you ready? We're going to derive the formula. We're going to show why that's true. Here it goes. So if I'm going to do this, think about a sphere, right? This ball. It's really like the top half of a circle rotated around the x-axis, isn't it? That's what it is. So if I were to look at this in two-dimensional space, if I were to imagine taking a circle, radius r, little r, and rotating just the top half of that circle around the x-axis, I would create this solid ball, wouldn't it? And I would get the volume. But there's a problem because a circle is not a function of x because it fails the vertical line test. So what I would need to do is somehow not look at the whole circle, but just maybe part of it. So how about I look at this? Half of it, I could probably even do one better. How about I just look at the first quadrant? Right there. If I take that piece and I rotate it around the x-axis, that would give me half of a ball, right? And whatever I get as an answer for that, I just double it, and that's the volume formula for total, for a sphere, for a ball. Wouldn't it be? Okay, so if I'm going to do this, though, I need to be able to come up with my outer radius and upper radius for my rectangle. Which means I need to know what the upper function is, what that one on the top is. We know it's a circle, but you need to give me more than that. I need it to be written as y equals a function of x. So how are you going to get it? If this is going to work. What is the equation of a circle? What is the equation of a circle centered at the origin with a radius of little r? So what's the equation of this circle right here? X squared plus y squared equals r squared. That's the equation of a circle centered at the origin, radius r. Can you solve that for y? Yes. So let's try. Y squared equals r squared minus x squared, right? And then finally solve for y's, take the square root. Now I should do plus or minus, shouldn't I? But because I'm only looking at the top half, right, I'm only going to take the positive square root, and that would give me the top half of the circle. Everyone agree with that? So over here, this red part, I could look at as y equals the positive root of r squared minus x squared. See, r here is a constant, right? X is our variable. R is some number that no one's telling me what it is. It's just some arbitrary, well, it's bigger than 0, or else it doesn't make sense to do the problem. All right, I'm not sure we really need to draw a reference, but I'm going to stick with what I've been doing. I'm going to rotate this around the x-axis, which means I'm going to draw a little axis here. I'm going to draw my little rectangle over here. What's the outer radius going to be here? It's that, right? It's the square root of r squared minus x squared. What's the inner radius? There is none, so 0, right? So down here, there's an inner radius of 0. So the bottom function for this one is y equals 0. Okay? Any questions? Can I go straight to the volume now? Yes? Okay, so the volume of that should be the pi, right? Don't forget the pi. Integral, where to where? 0 to r, right? 0 to little r of the outer function, or the outer radius function squared. That's a lifesaver right there. I love the fact that it's squared, because when I square that, what happens? You just get r squared minus x squared. Then minus the bottom function squared, but that's just 0, so it doesn't even need to be there. So I just going to write dx. Is that all right? And now we integrate. And I can do term-by-term integration. What is the antiderivative of r squared? R squared is a constant. So what's the antiderivative of a constant? So here it is. What's the antiderivative of r squared if r is a constant? R squared x. R squared x. R squared x, right? R squared is a number. 10. Antiderivative of 10, 10x. Now, the antiderivative of x squared is 1/3 x cubed, because x is our variable. So I have minus 1/3 x cubed. And then I'm going to evaluate that from 0 to r. And I'm replacing what with r here? X, right? Replace the x with r. So what would we get? Let's see. R cubed first, minus 1/3 r cubed. And then what would happen if I plug in 0? You get 0, so there's nothing there. So what's r cubed take away 1/3 r cubed? 2/3 r cubed. So I've got pi times 2/3 r cubed, which is the same as 2/3 pi r cubed. But remember, this was only half of it, right? This was only half of it. So if I want the whole thing, I just double this answer. We're done. Right? Let's do one. Yeah. Okay, does everyone get the basic idea of rotating a function around the x-axis? We have a case like this where it's really just one function, the other function is 0. And then the previous problem, we had two functions. And so we had an upper or a top square and a bottom square that we had to take into account. Now what I'm going to do is I'm going to tweak the problem a little bit. I'm going to instead of rotating around the x-axis, we're going to rotate around a different line. Because the x-axis is a line, isn't it? It's the line y equals 0. Now I'm going to shift that line somewhere else. And let's see if we can handle it. So I'll start with the new example. Oh, I should probably put on here, hold on. I should finish this up. This was half, right, of the ball. So 2 times 2/3 pi r cubed. If we double it, we get our 4/3 pi r cubed, which is the formula you would find in a reference sheet, right? That's kind of cool, huh? All right, so instructions here. Find volume of solid generated by rotating region bounded by y equals x squared, y equals the square root of x, and x equals 1 about the line y equals -4. Y equals -4 is a horizontal line, right? All right, so I'm going to start with a picture. I need to know what x squared looks like. I need to know what square root of x looks like. I need to know what x equals 1 looks like. I feel pretty good about that. I hope you do too. Here it comes. I'll try, yeah, I guess this will work. I think I'll draw my own. I'm doing it like this because I need to go down to y equals -4. So that's why I'm giving myself a little bit more y-axis in the negative direction. X squared looks like this. The square root of x looks like this. X equals 1. Vertical line through 1. But they hit each other at 1, don't they? So it was closed off anyway. Did I really need x equals 1? No. So let's erase it. I don't think we don't need it. I'm kind of making these problems up as I go, so I'm overthought that one. Okay, that good? That's our two functions. We want the region bounded by those two. So we want this, but we want to rotate it not around the x-axis, but around the line y equals -4. So I'm going to come down 1, 2, 3, 4, -4, and this is my axis of rotation. Now, are we going to get a different volume rotating it around that axis than we would if we rotate it around the x-axis? Absolutely, right? Because, look, if we rotate this around the x-axis, it's going to be very small, isn't it? Small little thing. But if we go around that y equals -4 way down there, now when you rotate it, you've got this huge hole in the middle, right? You've got a lot of volume on the outside now. You could practically jump through the hoop. Whereas if you rotate around the x-axis, you actually don't have a hole that you could go through. So it's totally different geometric shapes. So I'm going to go with the same procedure. I'm going to draw my vertical rectangle right here. I'm going to come out to the side. I'm going to draw my axis of rotation again. I'm going to draw my rectangle up here. I'm also going to put in here the x-axis. So that's my x-axis. This was y is -4 down here, right? Okay, now the idea behind the formula is this. When I rotate this, I'm getting this washer, right? The formula says volume is going to be pi integral a to b, and then it was the outer radius squared, right? Minus the inner radius squared. Your outer radius is the radius that goes from your axis of rotation all the way to the outside of the washer. So remember, your washer looks like this on the outside. It's going to go off the page. Let me bring it down. It goes like this. All right. Your washer looks something like this. No, it's terrible. It was supposed to be up here. All right. Okay, right up there. Rotation, right about there. Okay. That's right. It's not going to hurt. You don't have to draw the washer, okay? But what I'm trying to get at is that the outer radius is from this line of rotation all the way out to here, right? So it's not just f, is it? It's not just that top function. It's more than that. So let me measure something here for us. I'm going to zoom in on this just a little bit. What is the distance all the way from here to here? We'll call this R out, right? That outer radius is actually, it's this function here, which is from the top to here. Now, what function was up there? This is the green one, wasn't it? And which function was that? Square root of x. See how I'm labeling this? That part is square root of x. So I know the distance from here to here is square root of x. But what's the distance from here to here? 4. And it's a distance, right? It's a distance. It's an absolute value. It's a magnitude, isn't it? It's how far away that thing is. And really, at the end of the day, it doesn't matter even if you put a -4 because you're going to square it. But let's get it right in terms of, talking about a distance. Okay, so that R out then is really what? I'm going to write it down below this. The R out is actually the square root of x, what? Plus 4. That's your outer radius. Y'all following that? Now, what's your inner radius? Well, now let me go to the bottom function. What's this bottom function right here? That's x squared, which means the distance from here to here is x squared. I already know that the distance from here to here is what? 4, which means the total distance, this Rn over here, is what? Rn, remember, goes all the way up here to down here. What is that? X squared plus 4. Now I can set up the integral. Does that kind of help clarify why it is that I like to draw a picture? Does that help a little more? That you have to kind of keep track of this a little bit? I'm going to give you another one after this. It's going to be even a little more complicated. Okay, so the volume will be pi integral where to where? 0 to 1. Okay, outer function squared. Square root of x plus 4 squared minus x squared plus 4 squared dx. And so to integrate this, I would first expand this out, right? Like I would square it, then I would square this, I would get all things together, I would do power rule on a bunch of those, and I'd be on my way and I'd be done. So dot, 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 meaning the rest is left to the reader. Setup is key, all right? There are going to be problems on the test where you will have to go all the way with it, like most likely on the area problems that I give you on the test. Find the area, you'll have to give me the answer. But when we get to things like this, a lot of it's going to be set up the integral, but don't evaluate it. Set it up, set it up, set it up. That way I can give you a bunch of them, and you don't have to waste time integrating, all right? Questions? Yeah. You don't have to waste test time. No. No, there's more. Yep, there's more than this, yep. We have 2 other things we're going to look at. All right, any questions? I want to do this problem. I want to come back up here. What happened? It's not that bad. Don't go. All right, that's fine. I'm just going to. So look, we're going to take this now. I'm going to do the problem again. But this time, instead of rotating around y equals -4, let's go y equals 3. Same exact problem, y equals 3 instead. We're only going to set it up. I'm sorry? It's positive 3. So let's see what it would be. Let's see what it'll be. Okay? What I don't want you to do is go with your gut, because sometimes, a lot of times, your gut at this point might be incorrect. Use the geometry, use the picture, all right? Until you're completely convinced. If you're 100% sure right now that it's going to be what you think it is, then that's great. But you don't want to risk your grade on a test unless you feel real good about it, right? All right, well, maybe you do. All right, so I'm going to draw it this way now. And give myself a little more room on the y there, on the positive direction. Here's my square root of x. Or that's not my square root of x, that's my x squared. And then my square root of x looks like this. The region I want to rotate is in here. The rectangle I want is in here. And y equals 3 is above the region, isn't it? It's like 1, 2, it's up here. Here's 3. Here's my axis of rotation. So I want you to know that's my axis of rotation, so I draw that little curved arrow. Some people draw it as a dotted line. That's fine also if you want your axis of rotation to be dotted, so you can distinguish it from everything else. I'm going to come out here on the side. Axis of rotation, x-axis. Draw your rectangle, which is down here now. You with me? Okay, we need to get an outer radius. The outer radius is the distance from the axis of rotation to the outer edge of the rectangle, right? Which is this distance from here to here. That's my R out, right? My R in is this distance. You see it? Any questions? I also want to put my little curvy pieces in there, so I'll zoom in. My little curved pieces, this was the square root, and this was the x squared down here, right? Okay. Who wants to tell me what R out is going to be? Go ahead. What's R out? I haven't heard it yet. What's the distance? What's the distance all the way from the axis of rotation all the way down to the x-axis? All the way to the x-axis. It's 3, isn't it? All the way? You don't want to go all the way. You want to go 3, but take away how much? That height right there, right? So you don't want to go all the way from here all the way down to 3. You want to take that 3 and take away this much. How much is this much? X squared. 3 minus x squared is that distance. So we're keeping in mind that from here to here is x squared, which means this R out is 3 minus x squared. You got to ask questions. If you're unclear on that, please. Mm-hmm. That's right, you could. Because of the squaring, it would resolve itself. It would look different, but because of the squaring, it would all come out to be the same. Yes? Well, that's a great question, okay? I want you to flip to the back page, okay, where I put in general right here, okay? See that box on the back of the first page says in general? You have V equals pi integral a to b. See how I say f outer squared minus f inner squared? You may as well change the f to r, because I've been using r in this class. These notes I made back in 2004. So I just happened to find them today, and I was like, I'll print them out. So change the f to r. It's not, see, look, to answer your question, Tyler, it's not about what's on top and bottom anymore. It's about actually understanding the geometry of, if you're standing on the axis of rotation, right? Let me get something out here. So let's just say I'm a person standing on this axis of rotation, right? And I'm looking out towards the rectangle that I want to rotate. I need to know the distance from me to that edge. That's now my outer radius. I don't care about top and bottom anymore, all right? And then this inner one is from me to that edge. Make sense? Okay, yes? If what was what? Like the top of the blue and the green line meet. If you move that down to where it would be touching the x-axis, you mean if this whole thing was down here? If this whole thing was below the x-axis, what would happen? Yes, I understand. Let's do that on the next problem. Okay? And then you can tell me. All right. All right. What's the inner? What's the inner? 3 minus the root x. So we know the distance from here to here is root x, and then that means that this inner is 3 minus root x. Now look, I am totally aware that there are some of you who have taken Cal 2 before, and you have seen this before, and this is a slightly different approach than what you may have been shown. There are multiple ways to approach this, all right? This is the way that I approach it. If you saw it a different way and you prefer the other way, then that's, you know. Who's been shown a different way? All right? Is it different, right? Okay, so I don't even want to get into it. I don't want to confuse people. Let me ask you, just you've seen a different way, honest answer, does this seem more complicated this way? Because you just more like applied a formula, or no? Yeah. Yeah, so it's a little less intuitive, I guess. It's just more of a plugging in thing, I guess. Yeah. Yeah, so the danger that the reason why I like to approach it this way is because I think it's very valuable to understand the geometry of what's happening, rather than just plug in. You know, that to me is dangerous. But if you like it that way, as long as you get the right answer, I'm not going to take off for it. Okay, we good? Set up the pi integral 0 to 1. Okay, outer 3 minus x squared, squared minus inner 3 minus root x squared dx. Dot, dot, dot. That if I say set up but do not evaluate, that's what you would do. On the exam, that's what I was saying. On the exam, what I'll do is I'll give you, most of my exams like this, what happens is I start out with two functions. I say find the area between the two. So you'd have to find that yellow area. Give me the answer. Then the next part would be, part B would be, now rotate around the x-axis, set up the integral but don't evaluate. Now rotate it around y equals -2. Set up but don't evaluate. Now rotate it around y equals 5. Set up but don't evaluate. Now rotate around the y-axis. Set up but don't evaluate. Now rotate around x equals something instead of y equals something. So I give you like one region and have you rotate it every possible scenario of rotation. Yeah. Okay. All right. Are we okay? Yes? All right, so the question was, what would happen if I have the same axis of rotation, right? But this region was down here below the x-axis. So what I'm going to do is I'm going to change these functions by subtracting 1 on both of them. And when I do that, that'll move them down. Okay? Oh, I want to do it this way. So I'm starting a new problem by request. Damn, where does the time go? So we go -1 square root of x minus 1. Now this is going to be a little trickier than what we just did, all right? But let's see what happens, all right? Yeah, let's see. Let me draw it all out first. Here's my axis of rotation, y equals 3 up here. My new region looks like this. Is it okay if I just draw the region and not the functions? Is that all right with you? And let me label them, though. The bottom one here was x squared minus 1, and the top one was square root of x minus 1. And I'm going to put my rectangle in here now. Axis of rotation, x-axis, rectangle is below it. I'm going to kind of exaggerate the rectangle being below. I'm going to move it down a little bit. Okay. Tell me about the outer radius. Going from here all the way down to here, right? That's R out. And then here, R in. What about R out? Let me label those things. On the bottom it was, what, x squared minus 1. And the top one was square root x minus 1. Yeah, there's something, yeah, it's subtle, but it's really important here. So I think hopefully everyone would agree that from here to here is what? 3, right? You just need to add this much. So you might initially think just add the function, right? Like from here to here is this function. So you just say add it. But that function lies where? Below the x-axis, meaning it's a negative number, isn't it? You subtract it. Add the negative. Okay? Think about it. If you plug in a number right here, like if I plug in a number right here, it's going to spit out a negative number. If I take that and add it to 3, it's actually going to be smaller than 3. That's not what I want. I want it to add to 3. So I need to account for that with the sign change. So this outer radius is going to be 3, not plus, but minus the x squared plus 1, or minus 1. Then the inner one, same concept, right? The inner one will be the full 3 and then minus this one. Pardon? We didn't use plus. We had to use minus here. That's what changed. Let me see. Where is it? Yeah, well, okay. But it's a different function, though. Yes. See, we did 3 minus x squared, but this one was x squared minus 1. So, yeah, they're different because the functions are different, which is why you would get a different number, which you should get a different answer, right? Because it's not the same geometric shape, right? It's moved down more. You wouldn't be able to resolve the what? The most you could do is you could just decide to shift the entire thing up, meaning you could just add one to this, add one to this, add one to this, move the whole thing up, and then you would do the same problem. Yeah. Translate it up one. Okay, let me finish with the formula. Volume will be pi integral what? 0 to 1. Okay, outer radius squared, 3 minus x minus 1, x squared minus 1, all that squared. I could have simplified that, right? I could have like distributed the negative through and collected like terms here, but I didn't. I'm just leaving it. Then minus the inner radius squared dx. Dot, dot, dot. Okay. Questions? We got to keep going. Okay, what about this? What about this? How about we want to do something like region bounded by x equals y squared, and then x equals eight minus y squared, about the y-axis. So I'm cutting out some of the wording here because I don't have time to write it. We want to take that region and we want to rotate around the y. Yes. Yes. Uh-huh. I thought I've said that now. No. No, no. On the setting up of the volume problems, it will be set up only. So you set the integral up. The downside of that is you'll have a lot of things to set up. Okay? So you'll have a region, you'll have to rotate it around 5 different things. So you have to set up 5 different integrals to show that you know the difference between the line being here and the line being here and the line being here and the line being here. All right? Knowing whether or not to use washers or shells, which we haven't talked about yet. So there's kind of a give and a take for it. But you will have to evaluate at least one, like an area problem. Okay, so rotate this around the y-axis. So let's draw it first. Notice that these are functions of y, not functions of x, which means they open up sideways, right? So the first one opens up like this. This one is x equals y squared. The other one, x equals 8 minus y squared, looks like this. And I want to go about the y-axis. Now, the problem we have here is that because these are functions of y and not functions of x, we can't use the method we just did, right? Our axis of rotation is the y-axis. We're trying to go around this way instead of around this way. So our washer needs to look different, right? Our rectangle can't be vertical. It has to be what? Horizontal. So I need to be able to get this to work out, this region in here. I need to be able to draw my rectangle sideways. So my rectangle is going to look like this. See the difference? And then rotate around the y-axis. Will that still give me a washer? Yes? It'll be flat though, right? If I rotate that around the x-axis? Yeah, but if I take it at the origin, I'm going to think maybe that the inner radius is 0. It's not 0, it changes, right? It's dictated by this bottom function. So I'm going to do, what I'm doing here is exactly what we just did, but now we're doing it sideways, okay? Right? I'm going around the y-axis, not the x. Okay, so below this, I'm going to draw my axis of rotation, which happens to be the y-axis. Okay, I'm going to rotate around this. I'm going to draw my rectangle to the right of it. A little over-exaggerated there. I'm going to draw the bottom function on it, which was the red one, and then the top function, which was the black one. Do y'all see how I'm doing basically the exact same thing, but sideways? And now I need to imagine wrapping that around. If I wrap that around, it would look like it's not easy to draw on glass, I'm telling you. Okay, that's what it would look like wrapped around, which is a washer, right? We're going to go C to D now. So tell me what this function here is. That's your 8 minus y squared, right? What's this one down here? Y squared. So the outer radius is from the axis of rotation out here. This is R out. So how far is that? 8 minus y squared. See, now it's a function of y instead of x. So this is 8 minus y squared. And then what's my inner radius here? R in is going to be just the y squared. We have any issues with that? No? All right. Then we set up the integral. But now that we're sideways, instead of going from A to B, we need to go from C to D like we did with areas, right? But that means I need to know where these two hit each other, don't I? Which means I need to go set up an intersection problem and figure out where they hit. So here's what I'll do right now. I have volume equals pi, integral C to D, I don't know yet. I'll come back and get those. It'll be my outer radius, 8 minus y squared, squared, minus my inner radius, which is y squared, squared, dy. Intersection. I set y minus 8 minus y squared equal to y squared, which means 8 equals 2y squared, which means 4 equals y squared, which means positive or negative 2 equals y. So that's just, I made it so it didn't work out to nice numbers. So negative 2 to 2? Yeah. Yep. Look, I'll point something else out after everyone's okay with this. Any issues? Okay. The reason why, there's a couple of reasons why, but look at, if I did a vertical rectangle here, look at, see my vertical rectangle? What's the top function that's hitting this? It's this one, right? What's the bottom one? It's the same one. And that's why a vertical rectangle wouldn't even come into play, because you have the same function on top and bottom. In order for this to work, you have to have different functions on the top and bottom. Or else you're subtracting the same thing, which would give you 0, which would mean 0. Where? 0 to 4. Uh-huh. 0 to 4 this way? Well, you mean the area from here down to the x-axis? You all the way here? You couldn't, because the top and bottom function are the same curve. It's the same curve on top and bottom. But the bigger picture is we're not trying to find the area, right? We're trying to find the volume. And we're trying to rotate around the y-axis. All right? So here's kind of a rule of thumb that we can use for this method with washers. If you're going to use washers, which means pi integral outer radius squared minus inner radius squared, if you're going to use that, the rectangle you draw must be perpendicular to your axis of rotation. Right? Look at this rectangle I drew is perpendicular to the axis of rotation. When I was trying to go around the x-axis here, the rectangle I drew is perpendicular to the axis of rotation. That's the way method of washers works. Only for washers. There's only one other method. And it's the method of shells. That's what I'm going to do for the next 20 minutes. The method of shells. Yes. Pardon? Yeah, that would cause some problems, wouldn't it? Because you would double. You'd be doubling a lot of things. So we never rotate through. Your axis of rotation never cuts through your region because it creates too much of an issue. Okay, are we good or not? This makes sense? Now, what would happen if I took this region? See, I don't know if I'm going to get to shells today. What if I take this same region? All right, let's do the same exact problem. But instead of around the y-axis, why don't I do it around x equals -2? X equals -2 is a vertical line, isn't it? So you would have that same region. That's probably the worst looking parabolas ever. That's our same region, right? I just cut the parabolas off, so you know. But now we're rotating around x is -2. So if I'm going to rotate around a vertical line, and I'm going to use washers, my rectangle is going to have to be perpendicular to that, right? So my rectangle will be in here like this. Come down here, I draw my axis of rotation, draw my y-axis, draw my rectangle, draw the curves, remembering that this one was 8 minus y squared, this one was y squared. So what's your outer radius? It's this all the way from here to here. So all we're doing is having to add 2, right? It was the 8 minus y squared, add 2 more. Because this distance from here to here is 2. It's like an absolute value distance. It's like, yeah, because you're measuring like how far from me to you. I'm not really taking into account the fact that it's a negative. All right? So this outer radius will be, what, 2 plus 8 minus y squared? What's the inner radius? 2 plus y squared. And so we set it up. Are there questions or not? Yes. Like putting it behind it? No, you can put it in the back, like plus 2 in the back. It wouldn't matter. Okay, so my volume would be pi integral. We still going from negative 2 to 2, right? Outer, which I'm going to write as 10 minus y squared. That was just too easy to simplify, right? 2 plus 8. That's my outer radius squared. Now my inner radius squared, 2 plus y squared, dy. And that would be the setup. All right, we've got 15 minutes. I want to at least talk about shells, all right? So let me see here. Yeah.
Like where x equals negative 2, if that was x equals positive 2, and where the rectangle is, if it was on the opposite side, would that mean 2 minus?
Okay, so you're saying if this was this, this was this, this was this, that was our region, right?
Yeah.
Our rectangle's in here, but our axis of rotation was over here. Is that what you're saying?
Yeah, and if, like, where the region is, if that was split across the middle.
On the other side also? Yeah, then we would have the distance would be from here to here, which would be whatever that distance is. But because it's on the other side, it's actually negative, right? Because it's on it, so you would be subtracting that. It would be just like the one that was asked where it's below the x-axis, same thing. You would have to account for that. So you got to pay attention, to what's going on. Like I addressed earlier, there is a way that you can do this where it's taught in a way where it is more of just like plug and chug, and you avoid a lot of this confusion. But again, to me, I think it's more valuable long term for a student to understand what's going on and be able to come up with the formula on their own rather than, it's kind of like that 4/3 pi r cubed, right? Did you see me reference anything? Did I pull anything out to prove that formula to you? No? It's the same sort of thing because I can derive it because I understand it at that level. Does that make sense? To come up with this and do the volume solid, I don't want you to know it because someone gave you a formula that you're just plugging something into. I want you to understand why it's that, right? Why is it that? Okay. Shells. So I'm trying to come up with a shape that will confuse you a little bit. Oh, here we go. All right, so how about this? I want you to do y equals x minus 2 squared, y equals 1. The region bounded by this, okay? Region bounded by this about the y-axis. I want that region bounded, that's BND, the region bounded by those two curves, I want you to rotate that around the y-axis. So does everyone know what x minus 2 squared looks like? It's the parabola x squared, but move to the right 2. Right? Because if you plug in 2, what do you get? 0, right? So you're on the x-axis. So it looks like this. 1, 2. Then it opens up like this. Y'all with me? Y equals 1 is where? Well, it's right here. So we got y equals 1, goes like this. Do y'all see the region? Yeah? Is it this? Okay. Now, I'll throw this in here. Some instructors don't do this method. All right, so I'm not sure. Everyone has their own prerogative. I think it's valuable, though. What issue are you going to run into if you try and do this with washers? Your axis of rotation, right, is this blue line, right? And if you're going to use washers, your rectangles have to be drawn perpendicular to that, don't they? So my rectangle would have to be in here like this. Bam, fail, right? What's wrong with that? It's the same function, right? So you're either going to have to somehow figure out how to draw that parabola and treat those somehow as functions of y instead of x, or you're going to have to use some other method, which is what the shells method is about. So here's what we're going to do. We're going to zoom in on this so you can see what I'm going to do. I am instead going to take a vertical rectangle. And the reason why I'm doing a vertical rectangle is because that's well defined. I have a top and I have a bottom, don't I? And I'm going to imagine wrapping that vertical rectangle around the y-axis. So I'll draw this below so you can see what comes of it. I have my y-axis here. I have my vertical rectangle here. And I'm going to wrap it around the y-axis. What do I get when I wrap that around the y-axis? What shape do I get? It's a washer, but remember I showed you there was like this kind of washer, and then there was this one, right? It's going to look more like this, isn't it? And remember there was a formula that I gave you for this. We had to do, instead of pi r squared, it was 2 pi h and then this thing, right? Remember that? 2 pi h and then this? Okay. Where was that? Here we go. Okay. So let's see. If I wrap that around, I'll draw it over here for you. It's going to look like this. That's what we'd have, right? If we did that, you agree? That's that thing wrapped around the y-axis. Cut that thing open and lay it out, and let's take a look at what it would give us. The volume of it, right? The volume of it is the 3 sides multiplied. So let's start with the thickness of it. Like how thick is this little thing right here? This piece. That's this thickness right here, isn't it? That thickness for us is the width of this rectangle. That's dx, isn't it? That's dx. It's going to become infinite, right? Infinitely small. So would you agree that's dx? Y'all on board or not? Yeah? Okay. Tell me how tall this thing is. How high is this? Well, that's the height of this, which is the height of this, which for us is the distance between these two, right? Which is the top function minus the bottom function, isn't it? It's that line minus the x minus 2 squared, right? So this is going to be the top function minus the bottom. Which, in this particular case, what's the top function? 1 minus, what's the bottom function? X minus 2 squared. How long is this thing? Now, this is the trickiest part. Well, we cut it and we laid it open, right? Which means we needed to know the radius. The radius is actually in this picture right here. Look at this picture. The radius is the distance from the axis of rotation to my vertical rectangle, right? That's what it is. That radius right there. But the radius is where I have positioned that rectangle, isn't it? Left and right. And that is always just the variable x, the left and right. What is x going to vary between in this integral? Between 1 and 2. So what we're saying is this this distance right here is x is our radius. And so this becomes the circumference, which is 2 pi r. So for us would be 2 pi x. We'll definitely have to do more of this next class, but okay, so what is the volume of this one little piece? It'll be 2 pi x times dx. Why don't I throw that in the back? And then what's that other piece in here? 1 minus x minus 2 squared. That is the volume of just that sliver. But I want to add them up, don't I? I want to add all of them up. So I come in here and I integrate. The true volume of the whole thing should be the integral. Is there anything I can pull out of this integral? Like, remember the last one we pulled out a pi? I can pull a 2 pi out of this one. That will always be the case. Now, what am I going to be integrating from where to where? What's your variable? X is your variable. What does x vary between? Wherever they hit each other, right? It's 1 and 2. I'll let you solve that yourself. Find the intersections. X goes from 1 to 2. So you'll go from 1 to 2 of that formula. Everything else that's there. Is it 1 and 3? Oh, yeah. I don't know. 2 is the middle. No, we want to go all the way. 3, yes. That's why everyone's like, what? What the hell? 1 to 3. Yeah, 1 to 2 would only take you halfway. You want to go all the way to the next intersection, which would be 3. Does that kind of make sense? All right, I just want you to look at the very last page of the handout that I gave you. I have a formula for that, shells. What it is, volume equals 2 pi integral a to b u rad, I'm going to put radius, f out, f in, du. Okay, that's the formula I have. But I really want you to see, we'll spend more time on this next class. I just want you to see that this is what we just did. 2 pi is always going to be on the outside. This u radius is going to correspond to the distance from the axis of rotation to your rectangle. In this case, it's x, but that's only because this was the y-axis. What if instead of rotating around the y-axis, I had rotated around this line over here? It would be x plus whatever that distance is. So that radius would change. Or if I put the line on this side, then it would be whatever this distance is, take away x. So I guess what I'm getting at is that radius may change from time to time. This right here, I don't know why I have out and in. It should really be top and bottom. But we'll do more of it next class. Some homework that you can get started on for this. We still have more to do in this section. So we'll probably spend half of next class doing more. You should do on page 378. Oh, 378. I said 78, and I wrote 73. One through 17 odds. So what I would do on those is I would just first try, draw the pictures, set up the integral first, do it for all 17, and then go back and start evaluating them. Because the setup part is the most important thing. There's a pretty good chance that when we come in next time, we'll have a quiz where I'll just give you something and I'll ask you to set up the integral. That's it, right? We're done for the week? Yes. Have a good day.